Ding. Right, so yesterday we saw some basic functions. So we saw forwards lists, which are starting with a head and then a tail, and eventually you reach the ends. They're just like in Haskell. And we saw some like typical Haskell functions. So the zap thing where you're combining two lists, a list of function and a list of values. And so the hope is that you have something like this, where you have one function and one value. And then you're getting a list with the same length, where you've applied each of your functions to your values. But of course, because you're using lists, you might have extra lengths here on one of these two, and then the argument is just thrown away when you're defining your zap.
And the output is going to be the length of whichever of the two is shorter.
Yeah.
Which is gnarly.
So the type is not telling you anything. I mean, you can probably figure it out because, as we were saying yesterday, there's just no way to manufacture these values, but you have basically no guarantees. Then we saw tail. So tail, you somewhat, I mean, from the description of a list saying that it's either empty or it has a head and a tail, you could assume that tail is only called on non-empty lists because you want to extract it. But because in Agda, all of your functions need to be total, meaning that no matter what argument you get, you need to be able to provide an output for it. You also need to handle the empty list case. But here we're lucky because list has a value that can be manufactured even if we don't have any values that can fit in that list. It's just the value of the empty list. So we return that as a default. It's a convention, but it's sort of breaking your expectations that a tail is always smaller than the list itself. It's not true.
And it's one of those funny things actually, where in a language that makes weak promises like Haskell, the decision to fail violently if you try and take head or tail of an empty list is actually a good one. Because if you've made that mistake, you want to find it. You don't want kind of downstream garbage to cause some other problem sooner or later. You want to know now that you've messed up. But better still, let's not mess up.
Yeah, and then we saw head where there's no way to recover. So we just don't have an S, so there's no way to return an S. So a common strategy might be to return maybe an S. And then if you don't have a value, then you return nothing. But again, if the list is non-empty, this time you have no guarantee whatsoever that this is just the head. It could still be just nothing. So it's kind of annoying also. It's, in a sense, the type is a bit too big for the function that you want to implement to be fully characterized by it.
Yeah. So, and this is always the problem. If you're trying to tell the truth, then you need language to be precise about what is true. Otherwise, you end up saying things which are blandly true, but not actually that useful. So to say, oh, you might get an element, well, big deal.
Yeah. So then we saw a common Haskell pattern to solve this issue is to introduce the type of non-empty lists. So you have these lists with at least one value, and they're defined as just having a tail always, and having a head always, and then there's a tail, which is just a normal list. And we can now implement heads by saying, well, I'm guaranteed to have a head, so I can just return it. Of course, if you, in a sense, head is giving you the first element in the list. If you want to implement the function that looks for the second element, then you need to introduce list2, a type with at least 2 elements to be guaranteed to always have an answer. If you want the third one, you need to introduce list3, etc. It just doesn't scale. It's really annoying to have. And even then, so what we sort of suggested at the end of yesterday's lecture is that it's not precise enough to solve our ZAP problem, because what we can guarantee with list1 is that this here is present, but then the tails can still have a different length. And so again, you will be throwing some information away. And I don't know that there's a nice way to show that, because
Well, except that when you try and define it, you end up, because the tail of list ones are ordinary lists, you end up just calling ordinary ZAP.
yeah, exactly.
So same problem.
So if you're defining this thing, I'm sorry, I'm not using interactive editing. You need to build a list1. So I know that for this, there's a single constructor, so I can use Control-C, Control-R for refine, and Agda looks at the type, says, okay, there's a single constructor, so if you want to build such a thing, you're going to have to start with this. So then I can do this. And then here, as Connor was saying, we're left with our usual problem. We have a list of functions, a list of values, and we want a list of results. And the only thing we can do is call the good old ZAP on it. And so we've moved the problem one layer down, but the problem is still there. So the idea then is, instead of defining list1, list2, list3, etc., we're going to define a generic list type, which is indexed by its length. So it's you will be able to instantiate it to 1, 2, 3, etc., to just say I have a list that has this specific size.
Yeah. So general message, the length's important, so make the type talk about it.
But to talk about the size of the list, well, first we need to have that notion of size. And we started with an empty buffer, so we're going to define really quickly the type of natural numbers. So the type of natural number is a standard type. So I declare it like this. It's a set. And then it has two constructors. I don't know if it was already in 103 4 years ago. No. So you can have 0, oh, lowercase maybe.
Yeah, I wouldn't call it just
0.
Yeah.
And so it can be either 0 or 1 plus another nut, the successor of another nut. So we just define these two constructors. So if you're 0, you're already a nut. And if you're the successor of something, well, you need to tell what that something is. So for instance, I can define this thing. They're painful, but this is 3, because it's 0 plus 1 plus 1 plus 1. It's 3. Oh yeah, and then I'm going to be talking about a lot of nuts, so let's just give ourselves a bunch of variables. Whenever these names show up unbound in a type, they will be automatically generalized as natural numbers. And then I can define the type of lists, list n. So the idea is still the same. List n will be parameterized by the type of values that go in the list. But then we want to say that on top of that, we also know what the length of the list is. And here, that's where the type annotations become a bit interesting. Instead of just saying, so let's go find this one, list n. Oops. If you remember the definition of list, okay.
Yeah.
Boop, boop, boop. Here we just add a type, but now we have what we call a family. We have an entire family of types. So for any natural number whatsoever, list nx applied to that natural number will itself define a type. But crucially, list nx alone doesn't really make sense as a type anymore, because you haven't specified what the length is. And then we have our two same constructors, because we're still defining just lists.
Why not copy and paste from above and then comment out and all of that? I think that's you started with something useful. So
Yeah.
keep doing it.
Let's try to jump. All right. So now I'm getting, if I just try to copy paste the code and load it, I'm getting an error message. And, oh, this is cut off compared to my laptop. Too many pixels here. Right, so it's complaining that the target of a constructor must be the data type applied to everything it needs. But here I'm defining list n, and the return type of nil is still list because I just copy pasted. So I need to fix that up. It's just a list n now. And now it's complaining because I was supposed to deliver a NAT to sets here, but I just, I didn't apply it, right? So in a type signature, you need to be building a type, right? But here, this thing applied to just X is a NAT to set. It's not a set. So it's not a valid value. So I need to apply it to something. And then I will have the same issue here. I need to name things. I need to apply them. I need to name them, etc. All right. So now we need to make some choices. Well, the alignment is going to be a whole lot of work.
It's going to get more out of whack before it gets better.
We'll see. So now we need to pick a bunch of natural numbers for each one of these. And we said that in our mind, so the invariant is that the index, the NAT index, is the length of the list. So if we have an empty list, the length is 0. Thank you. Oh, I need to write it like this. I can fill in 0. And then if I have a head and a tail, I'm building a list that's one element bigger, but that works at any length whatsoever, right? It's a completely generic operation. So what we need to do is, that's kind of annoying. Maybe I can do it like this. No matter what length we had for the tail, we can put a head in front of it, and then it's going to build a list that's one bigger. Okay?
So what we're saying here is that universal quantifier, the upside down A, says this works for any n, and the curly braces mean we would quite like the n to be kept hidden from us. We don't want that n in our faces. The way we use nil and cons will look the same as for ordinary lists, but the type knows more about them.
Yeah, so here I'm not only saying I don't want to say what the type of n is because it shows up as the second argument to list n, so you should be able to figure out that it's a natural number. And also with the curly braces, I'm saying I don't want to fill it in when I'm building my list because, again, you should be able to figure out the size of the list based on the size of the tail. You just add 1 every time you add a constructor. So I can build a quick list n string of size 3.
You haven't done the pragma yet.
Oh, yeah. Oh. Luckily, I prepared one earlier.
Yes. It's worth noticing that these kind of 1 potato, 2 potato numbers are not ideal for the practical business of multiplying 642 by 557. However, they're quite useful for imagining stuff about things which build up one at a time. So these are numbers we might use for thinking about proof by induction rather than numbers we will use for difficult calculations at runtime. Right? You don't want your spreadsheet to use these numbers. And also, we're pretty much rapidly learning that we don't want to type them in either. There's a way around that.
There's some magic. Yeah.
So,
So here I was trying to write an example and I get a horrible error message, and it's not even a typer, it's a parser, so it's
Yeah.
even before that, and it's telling me that it cannot figure out what the meaning of this is, and the only thing it knows is that this thing is infix, because actually we didn't mention it yesterday, but when you define something with underscores here, there are no spaces. This is very important. You're saying, I'm defining a new identifier, and every single underscore is a spot for a value to go in. And these can be arbitrary. You can have like extra things around. You can have just as many as you want. They just need to make sense in the context. So here we have 4 holes. We have 2 arguments. That's not very good notation. You could write it, but it's just a bit silly.
yes. So Agda gives you plenty of rope to make up completely batshit notation. Be careful how you use this power.
Yeah, I've tried to restrain myself in the coursework.
Yes.
So we didn't say anything.
Notorious worst criminal in community.
We didn't say anything. So by default, Agda said, okay, it's infix. I can see that because you're using a bunch of underscores. And then I'm just going to pick some random level 20. And the problem now is that we have this expression, right? And it could mean, if I can find, where did I put the choke? Oh, yep. So we have hello, space,
Yeah.
and then world, and then, and there are 3 occurrences of this. So the parens, like the grouping, could go all the way to the left, right? It could go all the way to the right, the way these things are nested. It could go a bit either way, like it could be this thing, and then this thing, and then this thing. So because we haven't described the way the nesting should happen, there are too many solutions, and then Agda is like, well, I don't know which one makes sense, so I'm not going to try anything. So the fix for that, of course, is to say what we mean. And here it makes sense to have this associate to the right, because if you look at the type, if you're building a list, you're using this constructor, well, the sublist is to the right. So if you use many of them, you will always be putting a thing of the same type to the right and not to the left. So you want all of the brackets to associate to the right. And then I need to pick some level, I don't know, just pick whatever. They start matching when you have more of them, because then it defines a priority order between the different symbols. All right, do you want to implement heads n?
Okay. Well, we need to decide what's going to be the type of head n. And we want to make sure that we only call head on lists where it makes sense to call head. So are we choosy about how long they are? What length do we really not want? We don't want 0. So if a number isn't 0, then it is a successor. So we can say for all, see, I'm not typing the Unicode for all because my fingers just won't do that, but you're allowed to spell it out. That would be the type of head n. And as ever, I blow my fingers up. What happened there? Did I?
It's the wrong goal.
Yes, it is the wrong goal, and I need to get out of doing that. Other people's keyboards.
Mm.
Right, here we go. Right. So what do we see? Once again, I've introduced in curly braces the big X for the element type and the little n for, well, now the predecessor of the length. And I've started to write, you know, head n x's equals question mark. That's to say, I've named the input, but I haven't really got my clue yet. Load the file. Let's start chatting with the type checker. Immediately, Control-C, Control-comma. That's show me what's going on. And you can see we've got an X and an N. They're not in scope. And we've got an X's, which is a list of a non-zero length excellent news. So now what happens when I say, please split X's into cases with Control-C, Control-C, there's only one case. Because what's going on is ACTA isn't just reading the list of constructors and building a case for each constructor. It's comparing the indices given back by the constructor to see whether they can possibly be consistent with the thing we're looking at. So it's figuring out that this input cannot be nil because a number cannot be 0 and a successor at the same time. So we get only the one case. We're very happy. Let's look. You can see we have a little x that is very much the type that we would like. So I say, please guess the answer, and it guesses correctly because there was only one thing in that type lying around. Okay, so that's that.
Mm-hmm.
Something, actually, it might be, should we do tail as well, just
Sure.
while I'm here? Before, no. Is it control? It's control.
Alt W.
Oof. I'm
Oh.
old-fashioned.
Oh.
That's the trouble. So we want to do the same thing with tail.
I guess here we have a bit of freedom, yeah.
Well, we are going to say, though, I think we know we want to take the tail of lists that are non-empty. And if we know that the tail is of length 1 plus n, we can say exactly what the length of the tail should be. Oh, needed a space there. Okay, so same situation, right? We know that our input is non-empty. We do case analysis on it. And now let's look again. We see not only does the only constructor that fits is a cons, but its length is exactly the length we want. So what's happening is the type checker is solving the equation between the index of the list we're looking at and the indices given back by each constructor in turn. It's saying 0 is a successor, that can't happen. It's saying successor of this is successor of that. That means this is that. So it's doing quite a lot of equation solving behind the scenes in order to split this problem up for you. So it's not just working through a list of the constructors, copying them out. It's actually doing some mathematics on the fly to help you out. X's fits in the hole. Okie dokie. Do you want to do Zap or?
You can do it if you want.
Okay.
Yeah. I'll do append.
Yes.
And
Cool. Yes, you'll need to. So back to Zap. You're now in a position to make some proper promises. I want to say the list of functions has the same length as the list of inputs. So I've got a variable n that can talk about what that length is. And as per Guillaume's picture, we can say make a promise about how long the output list is. If only I can type. Okay. So let's see where we are. The important lesson coming up. At the moment, all we know about the length of the input is that they are n. We don't know what n is yet. So when we proceed as before and inspect our list of functions to see if it's empty or not, it might be, it might not be. We don't know what n is. So split. Now, something just happened. When we found that the list of functions was nil, we learned something about n. We learned that n had to be 0. And now look at our list of inputs. Its type just got more specific. Because we deduced that n had to be 0, we figured out that the list of inputs has to be of length 0 as well, and we want 0 outputs. In fact, I could write the same program I wrote before, and gratuitously I will. We now know that nil goes in this hole. But if we wanted to check, maybe we should check actually. Let's look at S's just to see what it is. No cons case, just nil. That's the only possible outcome. So that's just for reassurance. Likewise, when we look in this hole, we've now learnt that we've got, let me just rename that X to F, otherwise it offends. What do you see? You see, we now know that we've got an F and some Fs. We've learned specifically that our list of inputs also has to be of length successor, and likewise the outputs. So now when we split S's, just like when we were defining head and tail, we get only a cons case. So now we know that we've got this bunch of jigsaw pieces. We've got n functions, we've got n inputs, and we've got a spare function and a spare input, and we want one more than n output. Dear Agda, please do this jigsaw. So, and I'll just reload that file to make sure that it gets that right. I mean, and that was the only thing that was readily assemblable from those pieces. So I felt fairly confident in just demanding it. All right. So what's happening here? This is the weird thing that never happens in well, the kind of Haskell you're used to anyway, where you have a look at one piece of input and you learn something perhaps indirectly about some other pieces of input. You do a bit of poking about with some data and the types of other things get more specific. because you can make deductions from what you've learned by the direct inspection, right? You get some indirect benefit from that as well. And that is weird, new, wonderful.
Yeah, so another thing to
When I say new, it's not that new. I mean, it's about a quarter of a century old.
An interesting thing to see here, right, is that so we're only considering the happy cases because we're completely eliminated all of the weird ragged cases. But additionally, we also give some information about the outputs. So not only are we not checking for errors on the inputs as we process them, we're outputting some information about the output, meaning that we can keep staying in that happy place where the invariants are enforced and everything just flows naturally without having to, well, in the list case, we had this default value we could use all the time, but otherwise we would need like the maybe monad everywhere, polluting our codes with all of this error handling. So it's really nice that we're not just constraining the inputs, we're also giving guarantees to the users after that. Okay, so let's look at another function that is manipulating these lists of known length, appends. We didn't define append for lists, but whatever, I guess. Ooh. So it's going to be taking two lists. Okay, so there are some choices we need to make. And returning a third list, which corresponds to putting the values of the first one first, and then the values of the second one second. So when I'm describing this, because, well, I suppose we could say, it's nasty. What?
Yeah, I think our types are S and T.
Yeah. Okay.
Yeah.
So if we're going to produce a list of S's, then because we're combining values from both the first one and the second one, both of these need to contain S's. So this is going to be S, and this is going to be S. And then for the length, well, this time around, we know that the length of the result will depend on the length of the inputs, right? Because we're grabbing the first one and then putting the second one next to it. So these can be arbitrary in a sense. I mean, we could constrain them to have a fixed size, but that doesn't really make sense. So let's just say this is going to be M, and this is going to be N. Ooh.
Yeah.
This is going to be N. I suppose we could insist on them being the same also, but again, it doesn't make sense to impose constraints that are not needed. Because then the function is not as general as possible. It's like writing append only for list of strings rather than arbitrary lists. And then the result here, well, so what happens to the length when we're putting two lists side by side? We're just adding the two lengths together, right? Because we're preserving all of the elements in the first one and then all of the elements in the second one. So we need a notion of addition for natural numbers, which I'm going to define promptly. So I'm going to make it also in fixed right, although I don't know whether that's what's done in the standard library.
Yeah, it's people at school are taught that plus is left associative. That's what calculators do, right? You do 2 plus 3, and that gives you already 5. Plus 7 gives you 12. So it's grouping it to the left because just that's the order that you're typing stuff in. And you can get on with the calculation sooner. Also, you're taught that 2 plus 5 minus 1 is 7 minus 1, not 2 plus 4.
Right, so I'm doing this because I have something in mind actually. So natural numbers, if you remember, are defined as this type with two constructors. So when you define a function over natural numbers, you're going to define it over its constructors. So you're going to have to match on one of the two values and then look at it, what it looks like. and it's common to define it by induction over the first value. But you could define another operator called something different over the second value, and then you could prove that the functions are equal, but that's
Another story.
not for today. So I'm looking at M by doing case analysis on it. If it's 0, well, 0 plus n will be n, as you'd expect. And this is why I wanted to make it associate to the right, because I want this thing to be equal to this thing. Oh, I need more. Right, so because, oh no, it would have been fine either way, right? Yeah, no, it would have been fine either way, never mind.
We'll get there in a minute.
Yeah. And if the first value is non-zero, so it's 1 plus something, well, what can I do? I can say, well, the result is going to be non-zero already. It's going to be 1 plus something. And what is it going to be 1 plus of? Well, the predecessor plus n. N is not modified. Like this. So here, I guess I could add parens explicitly, but because plus is infix, this is not ambiguous, right? This is suc m plus n is suc m plus n.
So one thing which is the same as Haskell is the ordinary application is always tighter than infix operators. So those parens are redundant. However, they're still good documentation.
And now that I know how to add two numbers, I can express my invariant in the type by saying, if I take a first list of size n, m and a second list of size n, then putting them side by side will give me a list of size m plus n. And so let's, okay, terrible names as always. So if I have my x's and my y's, how do I append things? Well, I'm appending them left to right. So just like in Haskell, I'm going to inspect x's first. There are two possible solutions. Either x's is empty, in which case we learn that m is 0, which is to say that the return type should be 0 plus m plus n, the size of the return type. And by definition, 0 plus n is n. So if you look at the type here, it has reduced already to n just by computation. And this is what we were mentioning yesterday. That's why all of the functions need to be total in ACTA, because you can see that here we just casually decided to run that function during type checking that we just defined up here to simplify the type. And now, because 0 plus n has computed away to n, I can just use y's as you'd expect. And it's accepted as is. And if we have a cons on this side, well, it's chosen terrible names. So maybe I'm going to do a bit of cleanup. So I can write it like this. So just like you have curly braces for declaring arguments you don't care about, you have curly braces to introduce these arguments back.
Yeah, this is so in an application, this is saying, I'm actually going to tell you this one for a change. And here we're just saying it so that we can pick a nice name.
Yeah, and unfortunately here, because this is infix, I need to move it to prefix notation, because now it's taking 3 arguments instead of 2. So there's not enough places to put them all, but whatever. So you can see, if you remember the type of this constructor, it was taking the size of the tail, and then the overall size is the successor of that. So if I jump back into this hole, you can see that the size of the tail x's is m, this m that we bound here. And the size of the overall goal is now successor of m plus n, because it was successor of m plus n, but by definition, it can reduce to popping the successor out. And so now I'm ready to build this thing. If I use refine, there's only a single possible constructor that will build something of size the successor of something. So Agda picks it, and then I think if I do search, yeah,
Yeah.
it will find everything. So if you do Control-C, Control-A outside of a goal, it will not just solve the goal you were in, because you are not in any goal. It will solve all of them, or attempt to solve all of them.
Sounds dangerous to me.
Mm-hmm.
The sorcerer's apprentice. Right. So what's there important to say here? It's that Agda doesn't know anything about numbers. It didn't go to high school. All it knows about numbers, it has learned from this file that we just created. We just invented numbers. We just invented addition. And the only thing Agda knows about addition is that it obeys the two rules there on
Oh, sorry,
further up.
I'm messing things up.
Yes. And the point then is that we were very careful to define a version of addition which would compute in exactly the way we wanted to make list append nice. And life isn't always like that.
Yeah, so case in point, we could have defined this plus prime here, where instead of looking at the first argument, we look at the second one. That's also a valid definition, right? M plus 0 is M. M plus successor of n is the successor of m plus n. It's still true. It still matches our intuition of what addition should be. But now if we try to write append with that notion of addition, well, we're going to run into trouble, right? Because append is still behaving the same way. You're still copying along the values from the left list until you reach the nil, and then you're popping in the values for the right list. So let's split on x's. So if we know that x is empty, what is the type of the goal now? Well, it's 0 plus prime n, but its plus prime is not actually looking at its first argument. So it doesn't really care that the first argument is 0. It's waiting to know what the second is. It's like, it's all well and good that this is 0, but what is n itself?
Yeah, no pattern to reduce, I'm stuck, is what's going on here.
And if
So it's not magic, it's just doing what you tell it. So our first definition of plus is taking, I like to think of numbers as being made by potatoes with a lemon at the end. And if you did CS 103 again, you would be taught that that's what numbers are. So this one, there's a lemon here, right? Then these turns into 5. By taking these potatoes there, those potatoes there, and that lemon. Yes. Whereas plus prime is getting 5 in a different way. Here's the lemon. What's happening is that potato's going there, that one's going there, and then this lot is going there. And one of these bits of potato management looks like concatenation, looks like appending, and the other one does not. You know? So that's why we pick the version of adding that is as much like appending as possible to make the operation of appending go nice. And this is one of the extra skills that shows up when you're designing types of things in this sort of situation, is that sometimes things which are logically equivalent give you better or worse pragmatics because of how the computation works out. So that's an acknowledged concern.
Yeah, in other words, we care a lot about structure. and data structures in particular. So if I try to fit in the y's here, it doesn't work because Agda doesn't know that these two things are equal. You could prove it, but then the computation is sort of getting stuck on the proof and it's not as nice. So in general, it's better to find the right definition for your use case. Also, there are other definitions of successor, right? These could go on the M, for instance, and you could be making recursive calls where the M is getting bigger and bigger and bigger until you reach the end.
Yeah.
And then that's sort of reversing the potatoes of one side onto the other one. Yeah.
Would it make better sense for doing it that way to look at cases of y's instead of x's?
Well, we can try, but
Yeah, you might.
the
You can do that, and then you'll get a different kind of computation. But you'll find it's not so difficult to keep the same left to right order. So not so easy to keep the same left to right order when you're appending. You'll find there's an operation you can define, but it won't be append.
yeah, so here we got n to be 0, m plus 0 reduces to m, so we can just feed in x's. And here we got the successor, so you can say, okay, successor, and then I'm going to use the magic again. So we got the value here, but you can see that we're not putting the first list first and the second list second. We are now reversing the second one onto, no, we're
No, you're
now,
just doing it the other way around.
oh yeah, appending the other way, yeah.
Yeah, so it's you get it is not even remotely a coincidence that the append operation does the same kind of potato handling as the add operation. In many ways, these kind of list-like things. What is a list of length n? You start with a sequence of potatoes that gives you n, and then you attach an element to each spud. That's all we're saying, is that a list n is a version of n whose potatoes have been decorated with elements. And then append is saying, well, however you add the undecorated potatoes, that's how you combine the decorated potatoes.
We don't really have time. I'm wondering whether I can do pairs or
Oh yeah, chop.
yes.
Oh, we
So
haven't got pairs yet. Yes.
I mean, we've seen records in Haskell, so it's a bit similar, basically. So you can define a records. This is fancy Unicode syntax, but it means times. So the idea is that you have a pair of an A and a B. And so it's defined a little bit like a dates type, except that we are saying records. And then there's a single constructor because records are just a collection of values. And we typically call this one comma because it's for pairing. And then we can say we have the first value A.
Field.
Oh yeah, otherwise it's going to complain at me. And then we are listing the fields that it has. And because we have a pair of things, we want first the A and then the B. And then if you want to try to see whether you can figure out how to do this, you should be able to write an appending, or it's split at in Haskell, I believe.
Yeah.
But this is the total and correct version, saying that if my list is known to have size m plus n, then I can split it into the first bit, which is of size n, and then the second bit, which is of size n, such that appending these two gives you this back. But we're not doing the such as, such that yet. And I think that's it for today.
Yeah,
Unless you-
cool.
Yep.